In this video, I want to have a look at integration by substitution for definite integrals. So the important thing when we're looking at definite integrals is that at the moment, our upper and lower bounds, so that 3 and 2 in this first example, at the moment they're in terms of x. But if we make a substitution, we have to adjust those so that they're in terms of u as well. So let's have a look at this example. For our first one, we've got u equals x squared minus 3. So we're going to start the same way we did with indefinite integrals. We're going to differentiate first. So we're going to differentiate u with respect to x, and that would give us 2x, which means that du is equal to 2x dx. Now, what that means, if we're substituting in here, is we'd have to manipulate this to be from 2 to 3 to a 2x, x squared minus 3 dx, so that we've got that 2x dx, which is here, which can be replaced by our du. But because of that 2, we'd have to compensate with a half out the front. Now, before we substitute u's in, off to the side, we're going to figure out our new bounds. So what we're going to do, we had when x was equal to 2, so that was our original lower bound, then u is going to be equal to 2 squared minus 3. So we're substituting 2 into this equation here. And then we can solve that, so 4 minus 3 would give us 1. And when x was equal to 3, so that's our upper bound, we'd have u is equal to 3 squared minus 3, which would give us 9 minus 3, which is 6. So when we substitute all our u's in, our new bounds are going to be 1 and 6. So that means our integral is going to become a half times the integral between 1 and 6 of u du, because this whole x squared minus 3 is u, and the 2x dx is du. And now we can integrate. So we'll have our half out the front still, and if we integrate u, we have u squared over 2, and that's between 6 and 1. So then we can substitute in, so we'll have a half outside of 6 squared over 2 minus 1 squared over 2. And if we simplify all of that, we'll end up with 8 3/4. Our second example asks us to use the substitution u equals x minus 3 to evaluate the integral between 3 of 4 of x times the square root of x minus 3 dx. So again, off to the side, we're going to do a pile of work before we even actually start integrating. So if we know that u is equal to x minus 3, that means that du dx would just be equal to 1, which means that du is equal to dx. Now if we look at our bounds, when x was 3, so our lower bound, that means that u would be equal to 3 minus 3, which is 0. And when x was 4, which is our upper bound, u would be equal to 4 minus 3, which is 1. So that's our new upper and lower bounds. So if we start having a look at this then, we've got the integral between 3 and 4 of x square root of x minus 3 dx. So what we've got is this x minus 3, that's just going to be our u here. We've also got that du is equal to dx. So this dx here is going to become just du here. But then we also have this x hanging out the front. And often in our examples we've looked at so far, that's combined with this dx to turn into du. But in this case, it's not going to. So what we're going to do instead is we're going to use this equation here, and we're going to rearrange it. So from there, we could write that x is equal to u plus 3. So that's what we're going to replace that x with. All right, so this is going to become an integral with our new bounds, so from 0 to 1, of u plus 3 times the square root of u du. Now I'm going to rewrite that u as with a power instead of a surd. So we're going to have between 0 and 1 of u plus 3, u to the power of a half du. And then I'm going to expand out. So we'd have the integral from 0 to 1 of u to the power of 3 over 2, because it's 1.5, plus 3u to the power of a half du. And now I can integrate. So I'm going to have u to the power of 5 over 2. And then if I divide by 5 over 2, that's the same as 2 over 5. And then I have plus, I've got 3u to the power of 3 over 2. And then I'd have to times by 2/3. So if I times by 2/3, those 3's are going to cancel out. So what I can write instead, if I take the shortcut, is just 2. And then we're going between 1 and 0. So when I substitute in, I'd have 2/5, substituting 1 in here, plus 2. And if I substitute 0 in, I'm going to get 0 for both. So that's my answer, and I can simplify that just to 2 and 2/5. For our last example, we're asked to evaluate the integral between 0 and 1 of t over the square root of t plus 1 dt using the substitution t equals u squared minus 1. So this isn't the form that our substitution is usually given to us in. It's usually got u as the subject. So we're going to rearrange this first. So if we know that t is u squared minus 1, then that means that u squared is t plus 1 and u is the square root of t plus 1. Now, to differentiate that, I'm going to first rewrite it with power of a half instead of the square root sign, and then I can differentiate. So du dt would be a half t plus 1 to the power of minus a half, which can be written as 1 over 2 root t plus 1. So if that's du dt, that means that du is going to be equal to 1 over 2 root t plus 1 dt. So you can see that here we've got that square root of t plus 1 in the denominator and the dt. So I'm going to have to manipulate it so it has that 2 in there as well. So let's do that first, and then we can figure out our new bounds. So if I go 0 to 1, t over 2 root t plus 1 dt. Because I put a 2 in the denominator, I'm going to have to compensate by putting a 2 out the front. So now I've manipulated it so that this t here can be replaced with this u squared minus 1, and this whole denominator and the dt can be replaced by du. So before we do those replacements, we need to figure out our new bounds. So when t was equal to 1, which was our upper bound, that means that u, using this formula here, is going to be equal to the square root of 1 plus 1, so the square root of 2. And when t was equal to 0, which was our lower bound, we're going to have u is equal to the square root of 0 plus 1, which is just the square root of 1, which is 1. So now we can substitute all of that in. So my integral is going to become 2 times the integral between 1 and root 2 of u squared minus 1 du. So now I can actually integrate it. So I'm going to have 2 outside of u cubed over 3 minus u with root 2 and 1. Now if I substitute in, I'm going to have 2 outside of root 2 cubed over 3 minus root 2 minus 1/3 minus 1. So now I want to simplify that down. So I'm going to have my 2 out the front. Now this root 2 cubed, I'm just going to write this down the bottom for a second. I could write that as root 2 times root 2 squared, because timesing together we'd add the powers together to get root 2 cubed. But root 2 squared is just 2, so I can write that as 2 root 2. So I can have this as 2 root 2 over 3 minus root 2 minus, and this section would give me minus 2/3. No, it wouldn't, sorry, because that bit in there would give me minus 2/3, but we've got that minus out the front, so that would give me a plus 2/3. Now to make this a little bit nicer, I'm going to pull my 3 out the front. So I'm going to have 2/3 outside of 2 root 2. So I've divided this bit by 3 by pulling it out the front. This bit I would have to have 3 root 2, so that when I expand it back out, I just end up with my root 2. And this one I would have 2. And then we can combine these like terms. So then I'm going to have as my final answer 2/3 outside of minus root 2 plus 2. So that's having a look at integration by substitution with definite integrals.